Okay, welcome. This is again another recorded lecture for chapter 5 here. Again, I'm just doing these to kind of keep us on track so that we can finish everything. Um, and again, you can watch these hopefully at your convenience and make sure you keep on pace with everything. So this lecture is going to continue on. I guess this would be chapter 5, part 3 in terms of numbering of these lectures. And part 1 was when we were last together live on Wednesday. Part 2 has already been posted. And in part 2, we talked about different ways to classify chemical reactions under sort of two big umbrellas, one being double displacement reactions, which included precipitation reactions and acid and base reactions. And the next sort of big umbrella was the redox reactions, which included things like synthesis and combination reactions, decomposition reactions, and single replacement reactions. So again, part 2 really covered the different ways to classify reactions. Part 1 of the lecture, when we were together live, covered balancing equations. And this one is going to pretty much try to put both of those things together. We're going to talk about moles, and we're going to talk about calculations that you can do from a balanced equation. But first off, we're going to talk about molar mass and Avogadro's number. And let's get started with that. So the first thing we're going to talk about is something that is known as the mole. And the mole, unfortunately, is not that little furry guy, but it is basically a unit in chemistry which represents a certain amount of something. So in life, we have a lot of words that represent a certain amount. So when we say we have a pair of something, that means we have 2 items. If we have a dozen, you give somebody a dozen roses, that's 12. If you find yourself a gross of pencils, and nobody talks about it too much, it's 144 pencils. So in chemistry, we actually do have a word that represents something, and that word is mole. And the abbreviation for mole is actually MOL. And not to be confused with this, sometimes people think this little abbreviation here will mean molecules, but it is the abbreviation for moles. So if somebody wants to talk about molecules, they will write out the word molecules. If you see MOL, it is the abbreviation for moles. Again, moles having to drop the E is the abbreviation that we got there. So what a mole is basically the amount of elementary substances that contain atoms, molecules, or particles, as there is in exactly the carbon-12 isotope. And if you remember, the carbon-12 isotope was the isotope that was chosen on the periodic table to figure out the atomic mass of elements. So if you remember, when we look on the periodic table underneath a symbol, the carbon-12 isotope was the one in which they compared all the other elements to come up with that value that we see on the bottom underneath the symbol on a periodic table. Now, the mole itself does represent a certain number. And just like a pair represents 2, a dozen represents 12, and a gross represents 144. When we say we have 1 mole of something, it represents this number, 6.022 times 10 to the 23. And this number, as we will see, is what is known as Avogadro's number. Now, when we talk about Avogadro's number, the units are different. In some cases, those units may be particles. In some cases, they may be atoms. Other cases, the units here may be molecules. Okay, maybe you got some pizzas. Sounds good right about now. You got some shoes, whatever it may be. But probably for us in chemistry, atoms and molecules are the 2 common units that we typically do see with Avogadro's number. And we'll come back to that, I think. When we talk about Avogadro's number, it is rounded usually to that 6.022 times 10 to the 23. Again, when we use this in a calculator, remember that when you put a number in scientific notation, make sure that you are using that exponent button on your calculator when you punch it in. And really what Avogadro's number is for us is a conversion factor. And it really is a conversion factor to go from moles to either atoms or molecules. And to do that conversion, we would start with moles. We would actually use Avogadro's number here on top. So on top would be 6.022 times 10 to the 23 atoms per mole. Moles will cancel, we'll be left with atoms. And we also can use Avogadro's number to go the other way if we have atoms, or again, if we have molecules, which is a common unit, and we want to go to moles, we would use Avogadro's number as well. So we would start with atoms, and we would divide here by Avogadro's number. It'd be 6.022 times 10 to the 23 atoms per mole. The atoms would cancel, you'd be left with moles. So essentially the way that we use Avogadro's number is just like that. It's going to be used as essentially a conversion factor to go between those units. So you're going to go from moles to atoms, or you may go from moles to molecules. We'll sort of talk about the distinction between those in just a second. Or again, if you have something in atoms or molecules and you need to convert them to moles, then obviously you would use Avogadro's number as well. Now, sometimes people, because they learned Avogadro's number, wants to always use it in like every calculation. I'm just going to use this number because, hey, I learned it, so I should. And you shouldn't do that. So you should not always use Avogadro's number in a calculation. Sometimes people do, and they do it wrong, obviously. The only time you should use Avogadro's number is in a case where you are either trying to find a number that's in the units of atoms or molecules, maybe particles as well. Or you're asked, well, you're asked this flying that, but or if you started with a number, that's in atoms, molecules, or particles. So if you don't see any of those keywords, you don't see atoms, you don't see molecules, you don't see particles, then you really should not use Avogadro's number. But if you're given a number that has atoms or molecules or particles, or you need to find a number with those units, then you definitely should use Avogadro's number. Now, what it means when we say Avogadro's number is you essentially can take anybody from the periodic table. So from the periodic table, you can take any element that you like. So for example, if we look at hydrogen, 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. Here we use atoms because hydrogen is an atom and an element by itself. That means you could write 2 conversion factors. You could write 1 mole of hydrogen over 6.022 times 10 to the 23 atoms of hydrogen. Or just like any conversion factor, you could do the opposite. You could take 6.022 times 10 to the 23 atoms of hydrogen over 1 mole. You could do that relationship for anybody. If I had 1 mole of iron, it would also contain 6.022 times 10 to the 23 atoms of hydrogen. Atoms of iron. You also, again, could write the same 2 conversion factors. 1 mole of copper would also contain 6.022 times 10 to the 23 atoms of copper. And again, you could write 2 conversion factors for that. One being 1 mole of copper over 6.022 times 10 to the 23 atoms of copper, are the opposite, 6.022 times 10 to the 23 atoms of copper over 1 mole. So again, from any of these relationships, you could get 2 conversion factors, and you most likely in a normal conversion problem like we've done before, you would not use both of them. You would choose the one based on dimensional analysis that you would need to use. Now, Avogadro's number is not also just limited to individual atoms. So, for example, if you had something like 1 mole of water. Now, water, which is H2O, is not just an atom of an element, it's actually a molecule. So that would mean that there are 6.022 times 10 to the 23. Avogadro's number doesn't change, but this would be molecules of water. Again, here, because water is not an atom, it's a molecule. So the only thing that really changes is the units associated with Avogadro's number. It becomes molecules instead of atoms. So that's what I was talking about earlier, that it could be atoms, those units, it could be molecules, could be particles, could be really any unit you want, but Avogadro's number will remain the same. That also means that you could write 2 conversion factors. 1 mole of water gives you 6.022 times 10 to the 23 molecules here of water. Since I'm out of room, I'll go to this side. Or you could write the opposite. You could put Avogadro's number up on top. So 6.022 times 10 to the 23 molecules of water and 1 mole of water. You could do that for any other type of molecule as well. If you had 1 mole of CH4, which is methane, it would also contain 6.022 times 10 to the 23 molecules of CH4. Again, from that, you could get your 2 conversion factors that you could write for that as well. So we could relate Avogadro's number both to atoms. We could also relate it both to molecules as well. Again, number will not change. It's just the units that will change as we sort of use Avogadro's number there. Now, this also relates to another sort of aspect of elements and molecules that we deal with, and this is what is known as molar mass. So when we talk about the molar mass of a substance, the units associated with molar mass, and change the color here just to mix it up a little bit. The units that we have associated with molar mass are grams per mole. So those are typically the units associated with molar mass. And the molar mass is basically the mass in grams per 1 mole of a element or of a substance. And the molar mass is actually, from the periodic table, the same number that we pull off for the atomic mass. So when we look at something like carbon, it says 12.01. What that means, the molar mass of carbon is 12.01 grams per mole. The number always stays with the grams part, and it's always per 1 mole. So when you do molar mass, it's always per 1 mole. It's basically this equality that there are 12.01 grams of carbon and 1 mole of carbon. And really, although if you were asked what the molar mass of carbon was, you pretty much would write it just like this. But essentially, just like Avogadro's number, we can essentially use molar mass as a conversion factor. And we use the molar mass as a conversion factor the same way as we can use Avogadro's number. So from that 12.01 grams per mole, we could say that there are 12.01 grams of carbon over 1 mole of carbon. Or we could say in 1 mole of carbon, there are 12.01 grams of carbon. So we could use them as a conversion factor for dimensional analysis. And molar mass is our conversion basically to go from grams to moles, which is a super important conversion in chemistry. It is one that we do a lot in a lot of different problems, especially later on this chapter as well. The first step is essentially to take grams and convert them to moles. So the molar mass from the periodic table is where we do that. And if we need to go the opposite way around, if we go from moles to grams, which is also something that we do a lot, the molar mass is our conversion factor to do that. So the way that we use molar mass to do that is very similar. If we started with grams and we divided by the molar mass from the periodic table, the grams would cancel and that would leave us with moles. So this is the conversion from going from grams to moles. This coming from the periodic table. And the other way we would do it is going from moles to grams. We would start with moles, use the molar mass, and multiply by it. Grams on top, moles on the bottom. Moles cancel, and we do get grams in this case. So molar mass, you could kind of think of it as sort of a conversion factor that is used to go from grams to moles and moles to grams. And anybody that you take off the periodic table, basically the atomic mass, so if you remember the atomic mass that we talked about earlier, was usually given in a unit known as AMU, which is an atomic mass unit. And that is the number that we see on the periodic table. And that number in AMU per atom is the exact same number as you get as grams per mole. So typically when we do pull a number off the periodic table here for molar mass, typically we take 4 significant figures. So depending on your periodic table, you may have a lot more numbers there. You may have a little bit less, but typically the general rule is when you pull off from the periodic table the molar mass of a substance, or you're trying to calculate the molar mass of a substance, what you do is typically take 4 significant figures. So we look at something like sodium, it says 2299 underneath sodium, and that would be 2299 grams per mole. So the molar mass of sodium over here, I stop hitting the buttons, do it one more time, is 2299 grams per mole. The molar mass of copper from the periodic table, if you look underneath it, 6355 grams per mole. And you could do that for anybody that you see on the periodic table. And here is the periodic table. And again, when we look at the periodic table, what we're talking about in terms of molar mass is all these numbers that are on the bottom. This periodic table rounded a little bit up front, but usually about 4 significant figures is what we take. So the relationship that we see is you could do molar mass for any of these elements. You could also do it for something that is not an element, but a molecule like we saw earlier. So for example, if we wanted the molar mass of water, what we need to do is basically just add up all the parts. So there's 2 hydrogens. Each hydrogen is 1.008 grams per mole. I will say on this periodic table, they rounded a little bit, but usually 1.008 is where we take it to. But in this case, you would take it to 1.01 plus 16 grams per mole for our oxygen, which would be over here. Again, the first several here, they rounded kind of weird, but usually 16.00, which would be 4 significant figures, is typically what we would take it to. So this represents our 2 hydrogens here, and this represents our 1 oxygen. And when we add up all that, we get 18.02 grams per mole, which would be the molar mass of water. Again, you could use it as a conversion factor just the way it looks. You could use the 18.02 grams on top, the 1 mole of water on the bottom. Or vice versa, you could use the 1 mole of water on top and the 18.02 grams on the bottom. Again, something like CH4 that we saw earlier, you could do the same thing. You would take 12.01, which is the molar mass of carbon on the periodic table. Again, usually should have an extra digit there. Like all these guys should have some extra digits. We also have 4 hydrogens, which we would take 1.008 grams per mole for our hydrogen. And when we add that together, grab my calculator here, 12.01 plus 4 times 1.008 gives us something like 16.04 grams per mole. And again, that would be the molar mass of our CH4. And again, you can use that as a conversion factor. You can either use it like it's written with the 16.04 grams on top and the 1 mole on top over the 16.04 grams on the bottom. Now, how this ties together molar mass with Avogadro's number is, for example, if I have 1 mole of hydrogen, that would equal 1.008 grams, and 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. While if I had 1 mole of water, that would equal, as we see from the top there, 18.02 grams of water. And in 1 mole of water, there would be 6.022 times 10 to the 23 molecules of water. So that is sort of how these two things are tied together. They're related to each other that way. 1 mole is sort of the one that binds you. So if you needed to go from grams all the way to atoms or grams all the way to molecules, you would have to use the molar mass first to convert to grams to moles. And then you would have to use Avogadro's number to go from moles to atoms or moles to molecules. And again, if you started with atoms or molecules and you wanted to get to grams, you would start with Avogadro's number to get you to moles, and then moles down to grams using the molar mass. So sometimes we do use both of these sort of relationships together. And that's what we see here. So this is silver. 1 mole of silver has a mass of 107.9 grams, and that would be the molar mass of silver. So we would say silver's molar mass is 107.9 grams per mole. Carbon, like we just talked about, would be 12.01 grams per mole. And sulfur would be 3206 grams per mole as the molar mass. And then 1 mole of any of these guys, 1 mole of silver would equal 6.022 times 10 to the 23 atoms of silver. 1 mole of our carbon, like we talked about, would be 6.022 times 10 to the 23 atoms of carbon. Now, when we go backwards here, is that one of those things that we passed over? This is why when we look at something like this, these all represent 1 mole of these substances. So these all represent 1 mole quantities of, for example, potassium dichromate, sodium chloride. We got some iron there. I think we got some sulfur over there. Now, although they all represent 1 mole of each of those things, it does appear like, hey, 1 mole is that much. 1 mole of this guy is only that much. This guy, 1 mole of this guy is like that much. So although they do represent a 1 mole quantity of each of these things, the reason why we do see sort of different amounts is, for example, when we look at 1 mole of sulfur, that represents 3207 grams. While if we look at 1 mole of sodium chloride, for example, sodium chloride from the periodic table is 2299 plus 3545 for our chlorine. That represents 58.44 grams. So although they all represent the same amount of something, like the same mole quantity, 1 mole of sulfur is different than 1 mole of sodium chloride, which is different than 1 mole of potassium dichromate in terms of how much it actually is. So if we again did the molar mass here, 2299 grams per mole, and that was from the periodic table, and that represents our sodium, we would add it to 3545 grams per mole, which represents our chlorine from the periodic table, and that's how we get our molar mass, which is basically 58.44 grams per mole. Now, for our purposes, we will consider ionic compounds. We will call it molar mass, but sometimes, and more correctly, sometimes people will not call molar mass. They will call it the formula mass sometimes. And sometimes formula mass is used for ionic compounds, because technically they're not sharing electrons, they're ionic. So sometimes people use formula mass instead of molar mass, but for us in here, we will use molar mass for everything ionic, covalent compounds. But you will sometimes see formula mass or something like that used. And again, formula mass is sometimes used for just ionic compounds in terms of, kind of their molar mass or atomic mass, and instead of molar mass. All right, let's get back to where we were. Another periodic table, another periodic table. So again, we could use Avogadro's number. And again, we only want to use it when it has something to do with atoms or molecules in the question. Again, if you don't see anything that involves atoms or molecules, do not use Avogadro's number. Reminder as well, when we do see MOL, that is moles. That is not molecules. So again, that is a very common sort of confusion that people have when they see that MOL in a problem. They automatically, for some reason, think molecules. So let's take a look at an example here. Excuse me. The question is, we want to know how many moles of helium are there in 5.46 grams of helium. So the idea here is we do not see anything. There's no mention of atoms. There's no mention of molecules, which automatically tells us no Avogadro's number here. So we do not need Avogadro's number in this. We're essentially doing the conversion where we're going from grams to moles. And again, the conversion that allows us to do that is the molar mass. And we get that from the periodic table. So if we go back, and I think there was a periodic table here, we go back to the periodic table and we look underneath helium. And again, on most periodic tables, there will be another number there, and it's a 3. And we will see that it says 4.003 underneath helium. And that means that the molar mass of helium is 4.003 grams per mole. And again, we could use this as a conversion factor. We could say 4.003 grams per mole of helium. Or we could do the opposite. A mole of helium is 4.003 grams. So if we sort of do this problem in dimensional analysis, we will start with our 5.46 grams of helium. Here, helium is on top. So to get rid of the grams of helium, we would want to use this conversion factor. I'm sorry, wrong one. We want to use this conversion factor over here. And that would put our grams on the bottom per mole of helium. The grams of helium will cancel each other out, and we will get 5.46 divided by 4.003 gives us 1.36 moles of helium. In terms of significant figures, it is related to our original number, which has 3 significant figures. This, which comes from the periodic table, is sort of considered a conversion factor, so we don't really worry too much about it in terms of significant figures and stuff like that. So I think we might have another one here. Kind of wrote over it here, but we'll take a look. We want to know in the second problem here, how many grams of zinc are there in 0.256 moles of zinc? And again here, there is no mention of atoms. There's no mention of molecules. So we do not need Avogadro's number. So the same thing here is the molar mass is our conversion factor. And again, that comes from the periodic table. And if you look underneath zinc, you will see this number here, 6539 grams per mole on the periodic table. Again, that is the molar mass. And again, we could use it in the opposite direction. So in this case, we're going to start with the 0.265 moles of zinc. In this case, moles are on top, so we want the moles on the bottom. So we'll use it just like it's written, moles on the bottom, 6539 grams on top. The moles will cancel each other out. And we will take 0.256 times 6539. I'll put 2 many decimals there. And we'll get something like 16.7 grams of zinc. So in these first two sort of problems, neither one of them mention anything about atoms or molecules, which means no need for Avogadro's number in any of these. It is just our molar mass, which, a reminder, that is how you go from grams to moles, or backwards. It is that molar mass from the periodic table, which is in grams per mole. That is your conversion factor. Now, when we do some type of molar mass for something that is a molecule, we always want to do it just based off the formula. And we'll talk a little bit more about that in just a second. But let's take a look at another example here. Now, in this case, what we're looking for is we want to know what is the mass in grams of one gold atom. And in this case, there is our magic word, atom. So that means that we do need to use Avogadro's number in this case, which is what we see right here. We do need to use that Avogadro's number. So Avogadro's number, again, is that conversion factor that allows you to go from moles to atoms or molecules and back. So in this case, we're going to use Avogadro's number, and we're going to put Avogadro's number on the bottom, 6.022 times 10 to the 23 atoms of gold in 1 mole of gold. So remember that if we take anything from the periodic table or any type of molecule, basically 1 mole of it, so 1 mole of gold in this case will equal 6.022 times 10 to the 23 atoms of gold, which obviously can give us our 2 conversion factors. We're going to use this one here. Now, you don't have to get an answer at this point, but if you did, the atoms would cancel. And if you did get an answer at this point, you would end up with something like 1.661 times 10 to the minus 24, making sure you use your exponent button, moles of gold, which is close to what we're looking for. But in this case, we're not really looking for moles, but we are looking for grams. So this is a case where we do have to not only use Avogadro's number here, but we also then need to go from moles to grams. So that conversion is what we've been doing on the last couple of problems and what we talked about before. At this point, what we then have to do is take our moles and go to grams. And now what we need to do that is the molar mass from the periodic table to do that. And if you look up gold on the periodic table, you will see that it has a molar mass of 197 grams per mole. Again, 4 significant figures from that number that's underneath the AU symbol will get you. And that's what we're going to use here as the next conversion factor. So moles are on top, so we want moles on the bottom so that they cancel. Will give us 197 grams on top. The moles will cancel at this point, and we will end up with, if I punched the right number in, probably would help. We will end up with 3.271 times 10 to the minus 22 grams of gold. And if you look at that number, you should hopefully recognize that that number is a very small number, which is what you would expect. Here we are talking about 1 individual gold atom. So obviously it should have a very, very small mass. Minus 22 means we're going to take this decimal and head 22 places in that direction and put a whole bunch of zeros in front of it. So that would give you a very, very, very small number. Now, I did this in steps. So I did one calculation, got an answer, took that answer, did another calculation, and that's perfectly fine to do. If you don't want to do that, you could do it all together in one big calculation and just go from here to here and do the calculation, which is perfectly fine as well. If you do get an answer like I got in the middle there, like we talked about before, you do want to kind of avoid rounding too much in that middle step so that you don't end up with a kind of weird answer at the end. You may be also wondering why maybe I took the answer to 4 significant figures. The reason I took the answer to 4 significant figures here is because if we had 1 gold atom, for example, much like if I had 1 pen sitting on the desk, as we talked about before, that is probably something that you would kind of count. So it would be more of an exact number, which means it could technically have as many significant figures as you like. So I chose 4 just because molar mass and everything like that's the 4 significant figures. But technically speaking, because of that, 1 individual gold atom is kind of an exact number. You technically could have ended the answer with as many significant figures as you want. Now, we've done a couple of calculations here that involve, individual atoms. You could also, as we've talked about, do these calculations with things that are more like molecules. So, for example, if we look at something, say, like if we had let's say we had 32.5 grams of C2H6, and we want to know how many molecules that would be. So when we approach this problem, the first key is we're looking for molecules. So that should automatically trigger, I need to use Avogadro's number somewhere in this calculation. So since Avogadro's number is 1 mole of C2H6 would equal 6.022 times 10 to the 23, the units here would be molecules in this case, because C2H6 is covalent. They're sharing electrons, so it is a molecule, not just an atom by itself. But now, in order to actually use that, we actually have to get the units into moles to begin with. And if we look over here, we are starting with units of grams. So before we could do this calculation, we do need to go from grams to moles first. And then we're going to go from moles to molecules. And sort of our decision tree here is to do this. We need the molar mass from the periodic table. And to do this conversion here, that is where we would use Avogadro's number. So the first thing that we need to do, get the molar mass of C2H6. So again, we go to the periodic table and we're just going to add up all the parts. So there are 2 carbons, each at 12.01 grams per mole from the periodic table. Let's put carbon here. Plus there are 6 hydrogens in this case, each hydrogen from the periodic table 1.008 grams per mole. And if we add up all that together, grab my calculator here. That is 3007. And that is 30.07 grams per mole would be the molar mass of our C2H6. And again, we're going to use that to do our first part of the conversion, which is 32.5 grams of C2H6. We're going to use this as a conversion factor. So here we want to get rid of grams, so we want to put the grams on the bottom. Remember that the number stays with the grams, and it's always 1 mole when you do molar mass. So the grams would cancel. Again, here you don't need to get an answer, but I will just to show it to you. And hit the right button. We will get 1.0808. I'm just going to take it to a couple digits here, not round too much yet. Moles of C2H6. So that's close to where we need. So we're to here. So the next step is we need to use Avogadro's number to take us to the final part, which is molecules. So using our relationship and Avogadro's number, in this case, we want moles to cancel. So since moles are on top, we're going to do 1 mole of C2H6 would equal 6.022 times 10 to the 23 molecules here, because these are molecules of our C2H6. And if we do that, we're going to take that number times it by Avogadro's number, 6.022. Make sure you hit your exponent button times 23. Again, you don't have to hit the multiplication button once you hit that exponent button or anything like that. And we will end up with 6.51 times 10 to the 23 molecules of C2H6. So again here, that is a big number. which we expect since we have a lot of grams of C2H6. Just like before, you could do this all in one step. You don't have to get that middle number here. You could just do one big calculation. Whoops, that middle number here. You could just continue on and do the calculation. So molar mass is used a lot. Avogadro's number, not as much as molar mass in chemistry. That conversion, really this first part of the conversion here, going from grams to moles or moles to grams, is something that you do a lot in chemistry. Occasionally Avogadro's number pops out, but more so in this chapter. But after this chapter, molar mass definitely used probably a lot more. So with that in mind, since we did talk about sort of balancing equations and everything in this chapter, so let's just say, for example, we had this equation here, H2 plus O2 gives us H2O. And obviously this is not balanced, so do a little bit of balancing, maybe a 2 there, maybe a 2 there. Yeah. And that should be balanced. Now, say we have some type of problem, which we will shortly, where you need to get the molar mass from the periodic table of water. Now, sometimes we will have an equation where you have to do some calculations from, which is known as stoichiometry, which we're going to talk about in this chapter. But in that process, you may have to go to the periodic table and actually calculate the molar mass, say, of water. And when you do that, the molar mass of water in this case would be 2 times our 1.008 grams per mole for our hydrogen, plus our 16 grams per mole from the periodic table for our oxygen. And that gives us 18.02 grams per mole as the molar mass. Now, when people see the formula and the equation, and they go to do molar mass, they always want to use this number into place. So they'll sometimes do either 18.02 and then times it by 2 because it's there, and get whatever you get there, 36-ish. So 3604. And that is wrong. Or sometimes people, when they do it, they will do the 4 hydrogens at 1.008 grams per mole plus 2 oxygens because there's a big 2 in front of it, also giving you that 36 number, which is wrong as well. Regardless if there's a coefficient in a balanced equation and you need the molar mass, the definition of molar mass is what we talked about earlier. The definition of molar mass is how many grams there are in basically 1 mole of something. So 1 mole of something, how many grams there are. And that means that the mole always has to be 1. And that means when you do the molar mass of anything, it is always from the formula, regardless if there's a coefficient in the balanced equation. So water would be our 18.02. If I had to do the molar mass of H2 in this formula, it would be just 2 times 1.008 grams per mole, which is the mass of the hydrogen. That extra 2 in front has no effect on the molar mass, and it would be 2.016 grams per mole. So we do not, in molar mass, no matter what this coefficient may be, we do not include it in the molar mass. We do include it sometimes in a calculation later, which is basically known as stoichiometry, which is in this chapter, and we're going to talk about. And that's really where you include it, but you do not include the coefficient from a balanced equation if you're asked to do the molar mass of a formula, in the molar mass. It is just strictly just take the formula, regardless of the coefficient that comes in front, and just add up all the parts from the periodic table. So that's something people do a lot, and they mess up a lot on that by trying to incorporate those coefficients into the molar mass. So again, just another example here is if we had, say, 12.2 grams of C2H6O, and we wanted to know how many moles that is. In this case, remember that when we look at it, this is moles, not molecules. So because that is not molecules, we do not need Avogadro's number here. We are simply going from grams to moles. And again, it is the molar mass from the periodic table. That is our conversion factor to do that. So just like before, we need to get the molar mass of C2H6O. So again, from the periodic table, we're just going to go basically and add up all the parts. And that means that we would have 2 times 12.01 for carbon. You don't have to write the element above it if you don't want to. 6 times 1.008 grams per mole for our hydrogens. And there's 1 oxygen, which would be 16 grams per mole for our oxygen. And again, the molar mass would be, if we add all that together, we got 2 times 12.01 plus 6 times 1.008 plus a 16 gets us 4607. And again, what that means is there are 46.07 grams for every 1 mole, which is our molar mass of C2H6O. And again, in this case, we're going to use this as a conversion factor. So starting with our grams, 12.2 grams of C2H6O, using our molar mass as a conversion factor. Since grams are on top, we want the grams on the bottom. Again, the number always stays with the grams part. It's always 1 mole. The grams will cancel each other out, and that would get us 12.2 divided by 4607.265, it looks like. 0.265 moles of C2H6O, and this would be our answer, since we, again, here are not looking for molecules, but are looking for moles. So again, this is something that you need to be able to do. You need to be able to go from grams to moles to atoms to molecules, back and forth. You need to be able to calculate the molar mass from the periodic table. Again, it could be just 1 element by itself, or you may have to add up all the parts like we did here. And that gives you, again, how many grams there are in 1 mole of that particular compound. And again, usually 4 significant figures is what we do when we calculate molar mass or pull the molar mass from the periodic table. All right, so we did a number of those examples, so hopefully that should help you. So we're going to get into just a little bit here of tying both of those concepts together. We're going to tie together grams, moles, and balancing equations to actually do some calculations from a balanced equation. And what this will allow us to do is basically figure out, for example, how much product we may make, how much reactants we may need. We could do some calculations if we just really know one piece of information about somebody in the balanced equation. So we'll be able to kind of figure, a lot of very common questions out based on some very little starting information. So the basis of this approach is when we look at a balanced equation, and none of this, which is stoichiometry, works if we don't have a balanced equation. We could look at these coefficients here, and we could say, for example, in this case, that this is 2 molecules of H2 react with 1 molecule of O2 to form 2 molecules of H2O. We could also say that there are 2 moles of H2 react with 1 mole of O2 gives us 2 moles of H2O. There's no tricky math going on. It is as simple as the actual numbers that we see here is where we get these numbers from. It's just the coefficients from the balanced equation. There's a conservation of mass, which means if we use 3604 grams of reactants, which is our starting material, we should also get 36.04 grams of product out. Now, in stoichiometry, really, for the most part, the relationship that we use is really what is referred to as the mole-to-mole relationship. So when we do stoichiometry, it is really this relationship here, this mole-to-mole relationship that we use, which should automatically tell you if we have things in grams, we oftentimes need to convert things to moles. And again, that molar mass from the periodic table is going to be our conversion factor to do that. So we use this sort of conversion a lot because we do need to get things into moles in order for this relationship to work. So what stoichiometry does is it answers a couple of questions. It just answers questions like, if we know how much product that we made, we could do some calculations and figure out how much of each reactant that we started with, and vice versa. If we know how much of the reactants we started with, we could figure out how much product that we would make. So using that mole-to-mole relationship is essentially how we do that, and that's what is sometimes referred to as the mole method. So in terms of reactants or products, you may be given the units of these guys in a wide variety of units. But whatever unit you're given, either the reactant or the product, pretty much when you do a stoichiometry problem, which is what we're talking about here, usually the very first step that you do is you need to convert whatever those units are into moles. And very common, you're given grams. So again, very common, the first step that you do is you take the grams and you convert them into moles, again, using that molar mass from the periodic table. Also means that if the units that are given to you are in moles to begin with, you would not do any conversion. So you don't want to unconvert it and then come back to it. So that's very important. And again, that's something sometimes people sort of trip up on. Now, what you see on the screen is basically the 5 steps that you can follow to sort of do all kinds of basic stoichiometry problems. And let's take a look at this. Really, the first thing is the first 2 guys are really combinations that occur. So if you happen to be given everything in words, you want to make sure that you first write down all the correct formulas. And you want to get all the correct formulas down first. So as we talked about when we were balancing equations, if you don't have the right actual chemical formulas, you will never be able to balance that equation a lot of times. So you'll have really difficulty in balancing that equation. The next thing you want to do, and none of the stoichiometry stuff will work, is you want to make sure that the equation is balanced. And that's super important. So don't go away, come back. So really, a lot of times you're really starting with this step, and that is so important when you're doing stoichiometry. None of these calculations will work correctly if you don't start with the balanced equation. So it's like really important. If you are given an equation to begin with, and there's no coefficients in that equation, you should take a moment and double check and make sure that the equation is balanced. Probably if you do see coefficients in the equation, it probably is a balanced equation, so you're probably okay. But definitely if you don't see any coefficients in that equation, you should then go back and double check. And really, so usually a lot of times you will be starting off right about here. The next thing that you very commonly need to do is take whatever units they give you and get them into moles. So it's really important to convert those units to moles. So if you have grams, you need to use the molar mass to get the moles. If you have some other unit, if you started in pounds, for example, you may have to go from pounds to grams and grams to moles. It could be any unit to start with, but the ultimate goal that you need to get to is moles. And again, none of this works if you don't have a balanced equation, nor if you can't get everything into moles. Now, once you have it into moles, really the kind of the third step here that we oftentimes do, again, because oftentimes we don't have to do this first step. When we get to this third step here, we will usually go to the balanced equation. And this is why in the previous step, everything has to be in moles. And we'll go to the balanced equation and find that mole to mole relationship. And the mole to mole relationship that you're trying to find is the two things you're interested in. The first thing you're interested in is, we should have circled the whole thing, is what they gave you. So really the first thing you're interested in is this guy right here, whatever they gave you in step number 2. The second thing is what you're trying to find. And that is the two things that you're interested in. And that is, as we saw in the previous one, for example, if we had this equation, let's say we were given the amount of H2 and we wanted to find how much H2O. The relationship would be for every 2 moles of H2 I throw in there, I get 2 moles of H2O out. And that is the mole to mole relationship. And what that essentially is going to do, which is basically the big stoichiometry step, the step people always freak about, is this basically going to allow you just to be a conversion factor, because it's going to allow you to go from H2 in this case to H2O, because you can't look up in a book and go, how many moles of H2 is there as H2O. This is where we get that conversion factor from. We get it from the balanced chemical equation. And that is really what the big stoichiometry step is right here. It is going to that equation and finding that mole to mole relationship. And the last thing you're going to do is really sort of step 4. And when you're at step 4, you will always be in the units of moles to begin with. So sometimes in problems, they don't want the answer in moles, but they want it, say, in grams. So you'll have to convert, say, moles to grams. Again, a lot of times using molar mass. But again, could be some other unit. They may want it in pounds, for example. So you may have to do a couple of conversions, may have to do one conversion, may not have to do any conversions if they want the answer in moles. So you have to do some type of conversion usually to finish the problem. And as we'll go through these different sort of problems, what you will see is it is really, honestly, most of the time, the same 4 steps. And like I said, usually this very first step up here, you don't really have to do too much. So step 1, which is balance the equation. Step 2, which is convert to moles. Step 3 is the mole to mole relationship. And step 4 is converting those moles into some other unit. And those are usually the common steps that you have to follow, when you do these stoichiometry problems. I know it's a lot of words, so we'll do some examples, obviously, in this chapter and sort of see it. So when we look at something like this in this equation here, from this one equation, just to kind of show you the stoichiometry of it, or the relationships that you could get, looking at our coefficients, these again are going to be our moles of each of these guys. We could say for every 2 moles of CO that we put in there, we get out 2 moles of CO2. We could also say for every 2 moles of CO we put in there, we need to put in there 1 mole of O2. And we could also say for every 1 mole of O2 that we put in there, we have to get out 2 moles of CO2. And again, all these numbers come from the coefficient. So again, not written here, but it's assumed to be 1. This here is a 2. Now, each of these are equal to each other. Clearly, for example, 2 does not equal 1. Even with my bad math, I think I remember that doesn't equal each other. But when we say equal to each other or stoichiometrically equal to each other, what we're essentially saying is proportion-wise. In order for this reaction to take place properly, we need to throw in there 2 moles of CO with 1 mole of O2. It's kind of like when you bake cookies, right? You need to throw in so much sugar, so much flour, so many eggs in order to make, say, a dozen cookies. That is what we mean when we talk about stoichiometrically equal to each other. In order for this reaction to take place properly, we need to put in there the certain sort of ratio, if you will, moles of our reactants to moles of our products to get our guys out. Now, for each of these equalities, we could actually write 2 conversion factors for each of them. So for our first one, we could say that there are 2 moles of CO over 2 moles of CO2. Or we could say for every 2 moles of CO2, there are 2 moles of CO. For our second one, we could say for every 2 moles of CO, there is 1 mole of O2. Or for 1 mole of O2, there is 2 moles of CO. For our last guy here, we could say for every 1 mole of O2, we will have 2 moles of CO2. Or for every 2 moles of CO2, we could get 1 mole of O2. From this one individual equation, we were able to get 1, 2, 3, 4, 5, and 6 different conversion factors that we can use. And we get those 6 different conversion factors from 1, 2, and 3 stoichiometric relationships to each other. Now, would we use all 6 of these conversion factors in a problem? No, we would not. Just like in a normal basic kind of stoichiometry, basic conversion problem, we would not use both of the conversion factors that we could use. We would just use one. So for example, if I said we had 32 moles of CO2, how many moles of O2 did we start with? So if we had this little kind of problem, we could follow our basic steps. So our basic step is we want to make sure that we have a balanced equation, which we do. The second step is to convert whatever they gave us into moles. And in this particular case, they gave us 32 moles of CO2. So we do not need to do that. It's already done. So again, you don't want to do any kind of weird thing like unconvert it from moles and then go back and reconvert it into moles. Then the third step is we would want to go to the balanced equation and find the two things we're interested in. So the two things we're interested in this made up problem is we have the moles of CO2 given to us, and we're trying to figure out how much O2. So it is this relationship that we would want. And in that case, it is right here. And that gave us two conversion factors that we could use. So now when we take our 32 moles of CO2, we want to get rid of CO2 to get the O2. That is the big stoichiometry part. We want to go from this guy, which is the only information we got, to our O2. And that means we want to get rid of the CO2. So we would want to use this conversion factor right here. So we would take 2 moles of CO2 on the bottom, 1 mole of O2 on top. That is the stoichiometry problem. That is the stoichiometry part. That's going to get rid of our CO2 and allow us to go from CO2 to O2. And we're going to divide it by 2, gives us 16 moles of O2. This would be step number 3. Now, step number 4 is convert moles to other units. In this particular case, we don't need to do that because we are actually interested in how many moles of O2. So sometimes you may not have to do that last step. And in this case, we don't. So this would be the answer. And what that number basically represents is, in order to produce 32 moles of CO2, we would have to put in there 16 moles of O2. And if everything went perfect, we should get out 32 moles of O2, 32 moles of CO2. These are the same basic 4 steps for stoichiometry problems that you always come across, no matter how crazy it may look, how complicated it may look, but it's really the same 4 steps. So I think for this recorded lecture, we're going to stop here, which again, we're getting close to the end of chapter 5. This is going to allow us to work on some stoichiometry problems and finish up chapter 5 and maybe part 4 of chapter 5 recording that may come out after this one. So again, I thank you for listening to this, to keep on track with everything. And again, we will stop here. And this will be up on Canvas shortly. Obviously, when you see it, you'll know it's there. And then obviously, I will probably do one more and finish up chapter 5. All right, until next time, thank you again and have a good one.